Okay, so let's continue with our discussion on the Bayesian rule. And then we know that we remember that we stopped here. PB given A equal to PB times PA given B divided by probability of PA, which can be represented as PB times PA given B plus PB supplement times PA given B supplement. Complement, let's put it this way. Yeah, complement, right? PB complement times PA given B complement. So we use this example to go through what we just discussed, the Bayesian rule with complement discussion. Assume that a particular method, drug that testing can have an accuracy of 99% if athletes are taking drugs. For athletes not taking drugs, the positive test is only 0.5%. In a particular sport event, suppose only 1 in 1,000 athletes may take this kind of drug. Now, suppose an athlete is selected at random and test shows positive for the drug. What is the probability of the athlete is actually taking the drug? Now you have to define a different event. If B denotes a athlete taking the drug and A denotes the event that individual test is positive, then we know that the probability of someone is taking a drug is PB is actually 1 out of 1,000. In a particular sport event, suppose only 1 out of 1,000 athletes may take this kind of drug, so PB is 0.001. And then we say that A is the event that the individual test is positive. Suppose someone takes a drug and then tested to be positive, the probability is 0.99. It says a particular method test can only have accuracy of 0.99 if athletes are taking drugs, right? That's why PA given B is 0.99. And then how about PA given B supplement? Says if the athlete is not taking the drugs, the positive test is 0.005. Says for athletes not taking the drugs, the positive test is only 0.5, right? So PA given B complement equal to 0.005. Now, once we have these numbers, we know that we can what we're trying to do is the probability that the athlete is actually taking the drug given the test is positive. So probability that the athlete is actually taking the drug given the test is positive equal to this expanded form with a complementary probability, right? So now, because we know PB and we know PA given B, and we know PB, we know PA given B, we also know A given B complement. How about PB complement? PB complement should be 1 minus PB, which is 1 minus 0.001, which is 0.999. So once you put all those numbers in there, you do the calculation, it's around 0.165. It's actually very low. So, so this just give you an example to show you that what is the probability the athlete is actually taking the drug, given the fact that the test shows positive. Okay, just be aware that I just want last comment here. Statistical methods based on the Bayesian rule is called Bayesian statistics with many applications. And then Bayesian inference is a powerful technique for machine learning. That's the reason we want to discuss what is Bayesian rule and what is Bayesian statistics. Okay, now we're going to move on to something slightly different. it's something called Monte Carlo sampling. Before we talk about Monte Carlo sampling, you should be aware of some definition of Markov chain. So what is Markov chain? Markov chain is a sequence of random variables that its next state will only depend on the current state and the transition probability. What does that mean? Independent of its past history. What does that mean? That essentially says what happens previous state would affect what's going to happen for current state. But whatever happened prior to previous state would not affect what's going to happen for current state. Okay, give you an example. It says tomorrow's weather, sunny or cloudy, etc., will only depend on the weather today, current state, and how it may change from today to tomorrow. It's not the weather yesterday or last week. This is a strong condition. You can see that it's a strong assumption. In certain cases, it might apply. In many cases, it may not apply. So in any case, Markov chain is a dynamic stochastical process that is next state will only contingent on current state and the transition probability from current state to next state. Whatever happens previously would not affect what's going to happen tomorrow or what's going to happen next state. That is the definition of Markov chain. So mathematically speaking, that is to say, okay, what's going to happen for next step, k plus 1 for random variable x? Let's assume that we can use x subscript of k plus 1 to state, to stands for what's going to happen for next state for random variable. And then we know, given the conditioning on that previously xk equal to sk, xk minus 1 equal to sk minus 1, etc., etc. This probability is the same as the probability that we only condition on xk equal to sk. What does that mean? It's a definition of Markov chain to see that whatever happened prior to current state doesn't matter for what's going to happen for next state. Okay, all the past states are irrelevant and do not appear in this equation. This is the definition of Markov chain, and the Markov chain is quite useful in many mathematical modeling methods. Now, let's look at the property of Markov chain. A useful property of a Markov chain is that its long-term state as k approaching infinity will forget their initial states, leading to a stationary distribution of pi theta for parameter theta. This is one property. So in order to estimate that random parameter theta, we need two things. One is the current theta, and the second thing is transition probability. We also call this transition probability as transition kernel from theta to a new estimated state, which is theta prime. That is to say, this t theta prime equals to probability of theta prime given theta. And then this the stationary pi theta has symmetric balance condition. That is just some property. That is to say, t theta prime times pi theta equals to t theta prime theta times pi theta prime. Okay, this is the definition for Monte Carlo. It's really Markov chain. We haven't gone through the Monte Carlo sampling quite yet, but now, in order to understand Monte Carlo sampling, you have to understand what is Markov chain. And there's a specific thing that is called Monte Carlo Markov chain, MCMC. So MCMC is a random sampling method, and then it uses the property of the long-term stationary distribution pi theta that we just discussed. To estimate the distribution of theta properly, what we need is would be two things. Number one, it is a proposal distribution, Q theta theta prime. Proposal distribution is something that is to propose a new theta prime from theta. And this distribution could be uniform distribution, could be Gaussian distribution that we discussed earlier. And then the second thing that we need for this distribution of theta is a criteria to accept or reject the move from theta to theta prime. One of the algorithms is called Metropolis-Hastings algorithm. It's also called the MH algorithm. So what you do is you to draw a random number of samples at a Bay distribution p theta. The MH algorithm starts with theta equal to theta 0, which is a random guess at k equal to 1, and draws candidate c theta hat, theta optimum, or theta star from the proposal distribution Q. Then calculates the ratio, which is p theta star times q theta star theta k minus 1 divided by p theta subscript k minus 1 times q theta k minus 1 theta star. So the move from theta k minus 1 to candidate theta star is accepted with a probability of R such that we can update the theta k to be theta star. Otherwise, the move is discarded and no change is made from theta k minus 1 to theta k. It's the same solution. So as we just discussed, you need a proposal distribution, and also you need criteria to accept or reject. When running the MH algorithm, actually, theta is typically a vector of multiple dimensions. Now let's look at more specific algorithm. So that is steps that you should be taking, which is the same thing as what we just discussed. But specifically, we want to have more application of the MH algorithm. Suppose that if the proposal distribution QAB is symmetric, so that QAB equal to QBA, then R becomes nothing but because of the symmetric, these would be cancelled. They are identical, so that we are trying to minimize p theta k divided by p theta k minus 1 and 1 to see that what happens previously and then what's new proposed theta star. Then the MH algorithm becomes a classic Metropolis algorithm. You can see that MH is Metropolis-Hastings. Non-original algorithm was Metropolis algorithm, which has a property of symmetric proposal distribution of QAB. So for example, if we use the normal distribution, because we know it's symmetric, as a proposal distribution, then we know it would be Metropolis algorithm. Now, one more special specific application, that is when R is 1, then it is something called Gibbs sampler. With a lot of software packages actually provide you this Gibbs sampler. Now you might be questioning, why do we want to learn this, right? Why do we need all this kind of random sampling algorithm? So reality is in many cases you want to take a random sample out of your data, and then question is, how can you come back with a random sample? You would have multiple ways to come back with a random sample. And then specifically, you can use Markov chain, MCMC sampling. You can use MH algorithm to do sampling. You could use Metropolis algorithm to do sampling. You could use a Gibbs sampler to do the sampling. That's really the purpose. Once you realize, once you realize, oh, I need a random sample a sampling method, then you would go to this approach. Okay. So when using MCMC simulation, Monte Carlo Markov chain simulations, such as the MH algorithm, the designed sample are reached as k equaling approaching infinity. Therefore, most simulations will discard some initial samples for a certain period. That is called burn-in period. However, the choice of such burn-in periods is mostly empirical. It's not as simple as you could find out. Okay, so just be aware that a lot of software that actually implemented pseudo-random number generator that can generate most of the commonly used probability distributions such as uniform, Gaussian, exponential, and many others. So remember that we discussed all these distributions earlier, but how can we generate these distributions? Now we leave this as an exercise. You can use R functionalities and try to draw 1,000 points samples that obey a Poisson distribution with a lambda equal to 4. And then once you do that, draw 1,000 random points, and then you try to visualize your samples using histogram to see if your sample indeed follow a Poisson distribution type of histogram. Type of graph. That would be an exercise for you. Okay. After this section, Markov chain Monte Carlo sampling, we want to discuss a new topic that's called entropy. So entropy is defined as, for a given probability distribution Px, the Shannon entropy H is defined as HP. It's just pay attention, there's a negative sign here, right? And then it's a probability distribution times log probability distribution sum of different realization of xi's. Sum them up for discrete distribution. And then for continuous, instead of using sum, you use integration. So the log usually is base 2, and then we know that p is between 0 and 1, so that we know HP would be something that larger than or equal to 0, measures the average amount of the information in the distribution. So because p is between 0 and 1, log p is actually less than 0. That's why less than 0 and this negative sign becomes positive, so that we know HP larger than or equal to 0, which measures the average amount of information in the distribution. We call it Shannon entropy. And then there's a different definition, that is, it's not quite different. It's relevant distribution that's called cross entropy. For two distribution Px and Qx, HPQ is a negative of integration of Px log Qx dx that measures the distance or similarity or dissimilarity between Px and Qx. So whenever that you were thinking, okay, I have two distribution, they kind of similar, but how can I know if they're similar or not? Now it's a perfect opportunity. You realize that you can use cross entropy to measure the similarity or dissimilarity of those two distributions, so that you would have a better or deeper understanding of your two distributions. Okay, we can discuss this in further detail, more example on Shannon entropy. So one definition here is something called KL divergence. That is the difference between those two distribution Px and Qx. We call it KL divergence, and the definition is Px log Px divided by Qx dx integration. So this one can be rewritten as, we know is that log x divided by y is log x minus log y, so that we could further expand this relationship so that it becomes this format, right? Based on definition, we know that negative px log qx dx is what? It's cross entropy. Remember this negative sign. If you flip to the previous page, this is cross entropy. So entropy, so that it is HPQ. So this is HPQ. And then what is this? This is missing a negative sign. Once you have a negative sign, then it's HP. So that's why this whole relationship is HPQ minus HP. It is indeed the difference between the cross entropy and Shannon entropy. So clearly, if Px equal to Qx, the KL divergence becomes 0. Now, it's a perfect exercise for you to use this discrete probability distribution to estimate HP, HQ, and HPQ. Again, here this definition, we're kind of using this continuous variable, but if you use, in order to answer this question exercise, right, you should be looking at a discrete definition. So essentially for each one of them, what's the probability, and you can calculate the log px and then sum them up. Don't forget this negative sign. So essentially for this probability, and then what is the log of this p, do the multiplication between the probability and the log px, and then sum them up for each realization. Now, once you calculate HP, HQ, and HPQ, so that you would be able to calculate KL divergence. This is the exercise. Okay, these are the reference. On top of that, you should realize that these introduction of mathematical modeling methods, it goes not only statistics and probability distribution, but also touched upon linear algebra at the earlier section of this chapter. In addition to that, we even talked about random sampling. So it's really actually, beyond that, we also talked about Bayesian rules, right? All of these are different branches of applied mathematics. So you should read the chapter and get a better sense of what's happening, and know some of the answers to the exercise. Do some homework and answer the questions of the exercises. So you could leverage some of the free software packages, including Axiom, Maxima, SymPy, and others. It's a list that you should take a look in the textbook. And then you should also review the data mining and machine learning software. In addition to that, just be aware for Gibbs sampler, whenever you need to use, you can look at WinBox, this package. So that's all that I planned for chapter 2. And we'll move on to next chapter in next session. Thank you.